Good evening, everybody. Welcome to SLU. You are tuning in to my Intro to Astro crash course, and tonight we are going to talk about the cosmic microwave background. It's this radiation that permeates all of space, hence the background term. And we are going to talk about where it came from, why it's here, how do we study it, why do we study it, all these exciting things. So, if you're joining me over at slu.com, you can see my screen share that I'll be sharing with you. That way you can kind of follow along with some diagrams that I've got and really get some glimpses of what we're talking about. So let me flip on my screen share. Here we go. And right now this is just, my dashboard on our website. I'll take you a little bit through the site later, but first let's talk about the cosmic microwave background. What on earth are we looking at? The term empty space, the vacuum of space, it seems kind of misleading when you consider how much stuff is actually permeating through that vacuum out there. Gas and dust, dark matter even, and also a bunch of relic radiation from the Big Bang. In every direction in space, also known as isotropic, is what we call the cosmic microwave background, or for short, I'm going to refer to it as the CMB. A Space.com article I was looking at earlier referred to the CMB as the fog at the beginning of time, and I just love that description of it. It is like a fog. If you've ever seen a visualization of it, or if you're following along with me and looking at the visualization now, it looks like a granular fog, very granulated, grainy, I guess is the word I'm going for. But it just is everywhere. Kind of like sugar spilled all over the countertop. If you are like me and you try to cook and bake, and you'll know that you spill sugar everywhere when you really don't want to, breadcrumbs included. But anyway, it just goes everywhere, but it kind of also forms these little clumps as well. So the question is, where did this all over radiation come from? The Big Bang Theory predicts that the universe came out of nothing in a rapid expansion of space-time. In the beginning, this early universe, before it fully expanded, was immensely hot. And as it expanded, the gas that permeated all of space-time cooled off. So the CMB is the leftover radiation, or this leftover heat, from the Big Bang expansion. When you picture the Big Bang, where we don't know what it came from, but picture a point in space that just blew up, and it was actually space that was growing. But the amount of heat that was shoved into this tiny point was so high. But then as it expanded, it cooled off, kind of the way if you're taking a really hot shower and the bathroom fills up with a lot of really hot steam, and you get out of the shower and it's nice and warm in there. As soon as you open that bathroom door, you instantly regret it, right? Because all of the hot air rushes out, your steam is permeating out into the hallway, you hit a wall of cold. So this is like the leftover heat from the Big Bang. And so as science usually goes, well, on a good day, as science usually goes, the theory of the CMB was predicted before it was discovered. It was predicted back in 1948 by three scientists, Ralph Alpherin, working with Robert Herman and George Gamow. They were working on Big Bang nucleosynthesis. And they predicted that when the Big Bang happened, that this radiation should be left over in space. And if we could find it, we could start to prove that the Big Bang theory was real and correct. In 1965, Arno Penzias and Robert Wilson accidentally proved this theory about the CMB in New Jersey. Yeah, Jersey. At the Bell Telephone Labs, Wilson and Penzias were working on a radio receiver, or radio telescope, and they turned it toward the sky, and they detected this excess noise that did not seem to come from any one single direction. It seemed to come from all over, and it was just kind of this dull noise. Kind of think of white noise on your television, or if you're, I mean, I guess we don't really have that so much anymore, but the old televisions used to have white noise. So it was kind of like this white noise all over. And coincidentally, right over at Princeton University, which is in New Jersey as well, there were researchers working on an experiment to find the CMB. They were trying to design an experiment to find it. So when they heard about the result from Penzias and Wilson, they immediately realized that they had just found the CMB. And so at the same time, Penzias and Wilson and the team at Princeton both published papers on it in the Astrophysical Journal. The Penzias and Wilson paper was detailing their observations of it, and the Princeton paper was working more on like the cosmological interpretation of it. So they were both really beneficial papers, but the Nobel Prize for this discovery ultimately went to Penzias and Wilson in 1978. So today, the CMB measures at just 2.73 Kelvin. So Kelvin is a temperature scale, similar to a Celsius temperature scale. And this is only, so 2.73 is 2.73 degrees above absolute zero. So absolute zero on the Kelvin scale. On the Celsius scale, this is where water freezes. But on the Kelvin scale, this is where all motion within an atom ceases. So this radiation, because it's only 2.73 Kelvin above absolute zero, it shines primarily in the microwave portion of the electromagnetic spectrum. So let's go over and look at the electromagnetic spectrum. And let me see how well you can see this. I wonder if I can zoom in a little bit. I'll try. Zoom in. Yeah, there we go. Perfect. Okay, so we're looking at the electromagnetic spectrum, and we've talked about it before, but it is a really complex topic. So we'll keep talking about it over and over again. But basically, when you think about light, the words heat, radiation, light, spectra, we're all talking about the same thing here. And this light travels in what we call a wavelength, which is the distance between the two peaks of a wave of light. So light is made up of photons, but they are wave-like particles. So it's a weird dichotomy, but the wavelength that light travels in depends on what kind of light it is. So if we have shorter wavelengths, we're talking about like X-rays and gamma rays and really high energy photons. When we talk about longer wavelengths, so think of like if you take your hand and you make like a wave motion, if it's moving up and down very quickly, we're talking about short wavelengths and high energy. If it's moving up and down very slowly, we're talking about long wavelengths and low energy photons. And that's where we get into like radio waves. And then moving up is microwaves, infrared, visible light, ultraviolet, etc. So you can see here that microwaves, obviously like a microwave oven or like a radar. So this is the kind of light that the CMB shines in this part of the electromagnetic spectrum is microwaves. So it's not something that we're going to see with the naked eye. We're unfortunately not going to see it on our slew telescopes, but you would see it with a radio receiver. This temperature is uniform. So, well, for the most part, we'll talk a little bit about this granulation and why it's not perfectly uniform, but for all intents and purposes, it is uniform all over, and it's uniform to better than 1 part in 1,000. It's a really compelling reason to interpret this radiation as leftover from the Big Bang, because it's really hard for scientists to imagine that one local source of radiation would be this uniform in all directions. And many scientists have tried to devise an alternate explanation for this radiation, but there just isn't one that describes it as well as the Big Bang theory. So this radiation has been emitted 13.7 billion years ago. The universe is 13.8 billion years old, and just a few 100,000 years after the Big Bang, long before stars and galaxies even existed, the CMB radiation was emitted. So if we move backwards, so we know that the CMB is 2.73 Kelvin right now. When the visible universe was half of the current size, so imagine about half of how big it is now, the CMB was twice as hot, so like 5 Kelvin. When the visible universe was 1/100th of its present size, the CMB was about 100 times hotter, so 273 degrees Kelvin. We're now talking about the temperature of like a really cold brown dwarf or a very, very hot Jupiter. Also, 32 degrees Fahrenheit, the temperature at which water freezes in the Fahrenheit scale on Earth's surface. When the visible universe was only 100 millionth its present size, the temperature was 273 million degrees above absolute zero. So back when the universe was just a teeny tiny little baby, the CMB was 273 million degrees Kelvin, and now it is only 2.73 degrees Kelvin. It's cooled off so much. When the CMB photons were initially moving through the early universe, you can kind of think about it as how light moves through our atmosphere. So optical light propagates our atmosphere, and clouds effectively scatter this light. While optical light moves freely through clear air, the clouds like obscure our light. They scatter it away. So on a cloudy day, we can look up and we see light out towards the clouds, but we can't see through clouds, right? So really thick clouds that are in our atmosphere, you can't see through them. They're opaque. So you see sort of like a wall of cloud. You only see the part of the cloud that is closest to your eyes. So picture the CMB like this. Cosmologists studying the CMB can look through much of the universe back to when it was opaque, back to just a few 100,000 years after the Big Bang. There's this wall of light, and it's called the surface of last scattering. It was the last time that most of the CMB photons were directly scattered off of matter in the early universe. So when the universe expanded, we had all this radiation, that's what the CMB is, but there was all of this gas, and it started to coalesce and form like dust particles, and then these particles got bigger and bigger, and they had gravitational pull, and we started making stars, which then started making star clusters, which started making galaxies. So this CMB was scattering off of all of this matter. And when the last time that most of the CMB photons were directly scattered is this wall of light. So cosmologists can study the CMB all the way back until when they were last scattered off of matter. We call this the last scattering. So if we look at, this is a diagram that's kind of trying to explain what I was talking about. So if you're looking up at the sky, we can only see the surface of the cloud where light was last scattered. So light is coming, so up by my arrow, pretend the sun is directly north. So the sun is coming through the clouds. It's scattering, it's scattering, it's scattering. And then here, it's done scattering. It hit the bottom of the cloud, it's no longer scattering, and you see the resultant light. You can't see through the cloud, you can only see that wall where the light was last scattered. So if we imagine this to be the universe, the Big Bang happened, we have inflation, a formation of a lot of things, we have the CMB spectrum, blah, 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 blah. 380,000 years, the CMB has its last scattering. So when cosmologists look back in time, the further away we look, the longer it took that light to travel to us. So now we're getting into the definition of a light year and the finite speed of light. So light travels at a finite speed. So if we say something is 5 light years away, that means that's a distance, and that means that object is at a distance where its light traveling at that finite speed would take 5 years to get to us. So if we look at something that's 5 light years away, we're seeing it as it was 5 years ago. If we look at something that's 13 billion light years away, we're seeing it as it was 13 billion years ago. And so when cosmologists look back through all of the CMB, they can see all the way back to the last scattering of it, which was just almost 400,000 years after the Big Bang started. So we're looking at the surface of last scatter. Kind of tricky, and it's hard for me to wrap my head around too, but it's what we call it. So when we make maps of the temperature of the CMB, we're mapping this surface of last scattering. And as we mentioned, one of the most striking features about the CMB is how uniform it is. Because if it wasn't so uniform, there might be other explanations for why it's like that. But it is super uniform, which is what makes us really think that it came from the Big Bang. And it's interesting because with how uniform it is, it takes very sensitive instruments to detect any sort of differences in the CMB temperature, any what we call fluctuations. So if we look, this is a really great image that there's 3 instruments that are really prominent in studying the CMB: COBE, WMAP, and Planck. And here's images taken throughout the year of the CMB. So this is radiation in the microwave, so radio receivers. And the back in 1992, this was the best we could do. And so you can see that there really does seem to be some fluctuation, but it's very large scale. When we get more detailed images, the better technology gets, we can really start to see the granulation, and the fluctuations are on much smaller scales than what it appeared back in 1992. And then now we have this beautiful Planck image from 2013 where you can really see all the detailed variations in the CMB. And so what this is showing is that even though overall the CMB is about 2.73 Kelvin in every direction, it's also within small scales, not actually exactly the same temperature in every direction. By studying these sorts of fluctuations, cosmologists can learn about the origins of galaxies. This is what the large-scale structure of galaxies and galaxy formation, this is how these galaxies, where the matter, when the CMB is, we're talking about the last scatter here, remember, so the last time it scattered off of matter. So we can study the large-scale structure here and see where clumping matter likely was at the time that the CMB last scattered off of it. We can measure the basic parameters of the Big Bang theory. And by studying detailed properties of this radiation, we can learn about, I did not mean to click on that link. Let's go back. Oh, that's not what I was trying to go back to. There we go. We can learn about conditions in the universe on very large scales and at really early times, because this radiation has traveled over such a large distance to get to us. So one of the other things I think that is really cool to think about is, I mentioned earlier, if you wanted to think about the CMB, you could think about the white noise that's coming through your TVs. And so one of the questions you might have is that white noise the CMB? Well, it turns out that about 1% or less is coming from the CMB. So no, the white noise is not radiation directly from the CMB, but a teeny tiny little bit of it is. So this cosmic microwave background radiation is what's left over after the Big Bang. So we started from this point of light, we expanded very quickly, and all of the heat that was in the universe, as it expanded, it cooled, and it cooled to the temperature we have today. And so because our universe, as we know it, is still expanding, we can expect that the CMB is going to keep cooling off. But because it's only cooled about 2.5 degrees since the universe was half the size it is now, it's not really going to cool on any noticeable scale. It's, I mean, it could be detected down to very, very tiny decimal places, but it's not going to cool to a very noticeable temperature. So you can kind of think of this as like an afterglow. I really loved the description of the fog from the beginning. I read another description called the afterglow of creation. It's the leftover heat. So one of my favorite sites for information also is physics.org, and one of the other ways that they describe this is they call it the oldest fossil in creation, which is really neat to think about. We study fossils all the way from the earliest times of the Earth, but the oldest fossil of the whole universe is the CMB. because it comes from just 380,000 years after the universe exploded into creation. It's also the coldest thing in the universe, down to 2.73 degrees above absolute zero, which absolute zero is the lowest possible temperature. So this is the coldest thing in the universe. It's kind of like, I'm reading like I'm not directly reading, but it came from physics.org, this like list of like cool things about the CMB. And they also call it a baby photo of the universe. So it's when, you have your newborn photos, and this is kind of like our newborn photo of our early universe. It accounts for 99.9% of all the particles of light in the universe. Only 0.1% of the light is from stars and nebulae and galaxies. It's really crazy to think about how we look at the night sky and we look through our telescopes and we see all of this light, all these points of light, and they only make up 0.1% because 99.9% of the light is hidden in these microwave photons from the CMB. So if you were able to put on like glasses that could show you the CMB in a visible sense, you would see the whole universe being like one uniform color pretty much. When radio astronomers Penzias and Wilson had first spotted it, funny story, they blamed it on birds. There were pigeons nesting inside their giant microwave horn at Bell Labs, and they thought that the noise came from pigeon droppings interfering with their signal. Turns out, as they would find out later and receive a Nobel Prize for, they had discovered this major CMB radiation, which was known for the Big Bang Theory. And so I'll just leave you with one thought tonight, that because this is all over space, remember that we on Earth are part of the space, and it is all over us. When I was speaking with someone today and we were talking about gravitational waves, and their mind was just boggled with the fact that when the gravitational waves were detected on Earth, that means that they went through us too. They weren't just detected by the laser scopes because they were, pointed towards it or something. Those gravitational waves permeated through all of space-time. And so we felt those, or we didn't feel them technically, but they went through us. And so think about the CMB as this 2.73 Kelvin radiation is going through you right now. It's sitting on your couch with you. It's in your cup of water. It's all over with you. And so one of the fun things to think about is like, if I could just see it, I would see it literally in front of my face. It's not like you would only see it if you looked up into the night sky. You would see it in between the stars. You would literally see it right in front of your face. So I'll leave you with that thought. The Chilescope is online. We are outshined a little bit by some moonlight tonight, but we are lucky to have it online, and we are looking at a nice galaxy right now. You can see its spiral structure. And so if you tune in next week, I will be talking about fast radio bursts and other weird signals that come to us from deep space. Specifically, Carl Sagan talks about one in his book, Pale Blue Dot, about these weird narrow wavelength signals. And so we're going to talk about those fun things next week, and what is a fast radio burst and why are they so confusing the scientists. So I hope you have a good week, and happy Valentine's Day, everybody. I also hope that you have had or are having a day full of love, and that love has permeated your life today the same way the CMB is also currently permeating your life. Have a great week. I'll see you next time. How do we study it? Why do we study it? All these exciting things. So if you're joining me over at slu.com, you can see my screen share that I'll be sharing with you. That way you can kind of follow along with some diagrams that I've got, and really get some glimpses of what we're talking about. So Let me flip on my screen share. Here we go. And right now, this is just, my dashboard. In every direction in space, also known as isotropic, is what we call the cosmic microwave background, or for short, I'm going to refer to it as the CMB. A space.com article I was looking at earlier referred to the CMB as the fog at the beginning of time. And I just love that description of it. It is like a fog. If you've ever seen a visualization of it, or if you're following along with me and looking at the visualization now, it looks like a grand... Good evening, everybody. Welcome to SLU. You are tuning in to my Intro to Astro crash course. And tonight we are going to talk about the cosmic microwave background. It's this radiation that permeates all of space, hence the background term. And we are going to talk about where it came from, why it's here. Granular fog, very granulated, grainy, I guess is the word I'm going for. But it just is everywhere. Kind of like sugar spilled all over the countertop. If you are like me and you try to cook and bake, and you'll know that you spill sugar everywhere when you really don't want to, breadcrumbs included. But anyway, it just goes everywhere, but it kind of also forms these little clumps as well. So on our website, I'll take you a little bit through the site later, but first let's talk about the cosmic microwave background. What on earth are we looking at? The term empty space, the vacuum of space, it seems kind of misleading when you consider how much stuff is actually permeating through that vacuum out there. Gas and dust, dark matter even, and also a bunch of relic radiation from the Big Bang.